It's pretty fascinating, isn't it? How sometimes the simplest ideas in tech, or what sounds simple, actually hide some real depth.
Yeah, definitely.
Like, take a concept you think is straightforward, but it turns out there's this kind of surprising twist right at its core.
Mm-hmm.
Today, we're doing a deep dive into exactly that, linked lists. You've probably heard the term, it's a fundamental data structure.
Right.
But we want to cut through the standard definitions and reveal this weird paradox, why they're so flexible in theory, but often, well, kind of slow in practice.
That's the mission, yeah, to really unpack the linked list.
We've pulled together a bunch of research, articles, our own notes, basically everything you need.
So we'll look at its core structure, definitely those performance quirks you mentioned,
Yeah.
and crucially why it's still so important even now in modern software.
Okay, so let's dive in. Moving past the textbook, what's the real, core difference? How does a linked list actually store data compared to something like an array?
Well, forget those neat rows in memory for a second. An array needs that, right? Contiguous blocks.
Yeah, side by side.
A linked list is different. It's linear, yes. But the order comes from connections, not physical placement.
Connections, okay?
Think of it like a treasure hunt. Seriously. Each clue is a node,
A node, right?
and each node has two things. The treasure, which is your actual data, and critically, the location of the next clue. That's a pointer, basically a memory address.
Ah, okay. So each clue points to the next one.
Exactly. You start at the beginning, the head node,
Yeah.
and you know you're at the end when a node points to nowhere, to NLL. That's the tail.
Got it. The treasure hunt analogy helps, so that node is the key piece.
Absolutely fundamental.
Uh-huh.
The atomic unit, it holds the data payload, whatever that might be, and that next pointer, literally the memory address for the node that follows it.
And this is the big difference from arrays, right?
Precisely. Linked list nodes aren't stored together. They can be scattered anywhere in memory, non-contiguous. They're only connected logically by these pointers, and that's what makes them so dynamic. You can easily add or remove nodes without shuffling everything around. They just grow or shrink naturally.
And I gather there isn't just one kind of linked list. It sounds like there are variations.
Oh yeah, definitely different flavors. It often comes down to trade-offs, space versus time, usually.
Like what are the main types we should know?
Well, the most basic is the singly linked list. That's what we've mostly described.
Okay.
Unidirectional. You can only follow the pointers forward. Simple, less memory overhead.
Makes sense.
Then you've got the doubly linked list. This one adds another pointer to each node, a pref pointer.
Ah, so it points backwards too.
Exactly.
Sure.
Lets you traverse forwards and backwards.
Yeah.
The big win here is if you know which node you want to delete, you can do it super fast. Like O1, time complexity, constant time.
Regardless of list size.
Yep. But the trade-off is, well, more memory for that extra pointer on every single node.
Okay, so singly, doubly. Any others?
The other common one is circular linked list. Here, the last node's next pointer doesn't point to NUL.
Where does it point?
It points back to the head, creates a loop.
Huh. Why would you want that?
It's perfect for cyclical things. Think about a music playlist on repeat, or in operating systems, task schedulers often use a round-robin approach. A circular list is ideal for that.
Right. Okay, that makes sense. But here's where you said it gets tricky. The performance paradox.
Yes, this is key.
On paper, insertion, deletion, they seem fast. Potentially O1 if you know where you are. But in reality, linked lists often lag behind arrays. Why?
It boils down to one crucial concept: cache locality.
Cache locality. Okay, unpack that.
So modern CPUs are incredibly fast, right?
Yeah.
But accessing main memory, your RAM, is relatively slow. There's a huge speed gap.
Yeah, I've heard that.
To bridge that gap, CPUs have small, super fast memory caches right on the chip. When the CPU needs data, it checks the cache first. If it's a cache hit, it's lightning fast.
And if it's not?
That's a cache miss. The CPU has to stall, wait, and fetch the data from slower main memory. Now, arrays benefit hugely from spatial locality.
Meaning because they're stored together.
Exactly. They're contiguous. When you access one element, the CPU often fetches its neighbors into the cache too, using something called cache lines and prefetching. So the next access is likely a fast cache hit.
Okay, arrays are cache-friendly.
Very. Linked lists, not so much. Their nodes are scattered all over memory, remember?
Right, non-contiguous.
So accessing one node tells you nothing about where the next one is physically located. You almost always get a cache miss when you follow the pointer. Plus, you have the overhead of pointer dereferencing actually following that memory address. The CPU spends a lot of time just waiting for data from RAM.
So the theory is great, but the hardware reality, It kind of bites.
Pretty much. It really highlights Bjarne Stroustrup's famous advice: measure, don't guess. Theoretical big O is important, but it doesn't always capture these crucial hardware interactions.
That's a really critical point. So if they have these performance drawbacks, why are linked lists still taught everywhere? Why are they still, relevant?
Because they have a killer feature: pointer stability.
Pointer stability.
Think about dynamic arrays, like a C++std.vector or a Python list. When they need to grow beyond their capacity, they often reallocate entirely. They find a new, bigger block of memory and copy everything over.
Right, and that invalidates any existing pointers or references to the old elements.
Exactly. But with a linked list, inserting or deleting a node never invalidates pointers to other nodes in the list. Their memory addresses don't change.
Okay. And that's important when?
It's critical in complex systems, especially concurrent ones, where different parts of the program might hold references to elements in the list. You need those references to remain valid.
Makes sense. Anything else?
Well, they're also fundamental building blocks for other important data structures.
Like what?
Stacks and queues, for instance. Implementing them with linked lists gives you really efficient O1, push-pop, or in queue-to-queue operations at the ends.
Okay.
Hash tables often use them for collision resolution through a technique called separate chaining. Basically, you link together all the items that hash to the same bucket.
Right, I've seen that.
And graphs. A common way to represent graphs is using adjacency lists, where each vertex has a linked list of its neighbors.
So they underpin a lot of other structures. Any everyday examples?
Yeah. Think about your web browser's back and forward buttons, that history, often managed with something like a doubly linked list. Or Undorito functionality in software, very common use case.
Okay. That makes it concrete.
Even OS test scheduling, as we mentioned, with circular lists.
So it really comes down to this tension, doesn't it? The elegance and flexibility in theory
Versus the practical hardware challenges, mainly the cache performance. So the takeaway for you, the listener, is this: dynamic arrays, your vectors, and standard lists, they're usually the better default choice for general collections because they play well with caches. Yeah. But linked lists are indispensable specialized tools. Reach for them when that pointer stability is non-negotiable, or when you're implementing those specific structures like queues or hash chains, or maybe if you're dealing with really large data items where the cost of copying them for an array resize would be prohibitive.
And the key is?
Profile and measure, always.
Yeah.
See how it actually performs in your specific situation. Don't just assume based on Big O.
Great advice. So here's something to think about. What really stands out to you about how these fundamental, almost hidden structures like linked lists quietly power so much of the tech we use every single day? And how does understanding these trade-offs, this tension between theory and hardware, maybe change how you look at the software world around you?